So, how exactly do you catch a millionaire fraudster when they're hiding in literally a billion lines of data? Think about it for a second. Modern organizations are generating millions, sometimes billions of transactions every single year. That old school image of an auditor, the one sitting in a dusty back room manually flipping through paper receipts with a calculator, yeah, that is physically impossible today. If a malicious actor decides to skim, say, just a few pennies off a million transactions, human eyes are absolutely never going to spot it. So how do we find the needle in an unimaginably large digital haystack?
Well, welcome to This Explainer. We're going to dive deep into information systems auditing. And honestly, we can just toss out that outdated, boring bean counter stereotype right now. What we're actually talking about here is a world of modern digital detectives. These folks are armed with sophisticated algorithms, automated scripts, and even wild mathematical phenomena that hunt down anomalies, secure networks, and catch bad actors right in the act.
Here's our roadmap for the investigation. First, the detective's toolkit. Then, catching fraud with math. Third, auditing the system lifecycle. Fourth, locking down the network. And finally, following the audit trail.
Okay, let's dive into this. Section 1, the detective's toolkit.
When you're dealing with massive data volumes, you just can't rely on human intuition alone. You need serious firepower. Enter CAATs, that's Computer Assisted Audit Techniques. Think of this as the ultimate magnifying glass for our digital detective. Because IT systems are incredibly complex and process transactions at literal light speed, human testing is practically useless for finding systemic fraud. CAATs, on the other hand, allow auditors to extract the right data, clean it up, and run automated tests that scan millions of rows in minutes, not weeks. It completely removes human error from the testing phase and reveals patterns that are just entirely invisible to the naked eye.
So, what does this arsenal actually look like? Well, on one end of the spectrum, you've got specialized, standalone software like ACL and IDEA. Now, these are expensive, licensed tools, but they come with these incredible built-in audit tests for things like duplicate detection and gap analysis, and they easily handle millions of rows. But hey, you don't always need an expensive license. Take Excel Power Query. It's widely accessible, handles huge datasets, assuming your computer doesn't catch fire trying to load them, right? And then there's SQL. SQL is a real game changer because it's completely free, has unlimited capacity, and lets the auditor directly interrogate the database. There are no middlemen, no clunky graphical interface limitations, just raw, direct access to the single source of truth. Moving right along to Section 2, Catching Fraud with Math. Now that we have our tools, what happens when we actually unleash them? I found this absolutely fascinating. When human beings try to commit fraud and just make up numbers, we are surprisingly bad at it. To understand why, we have to travel all the way back to 1881. An astronomer named Simon Newcomb was looking through these old books of logarithm tables, and he noticed something super bizarre. The pages at the beginning of the book, so for numbers starting with 1, 2, and 3, they were incredibly worn out and smudged from heavy use. But the pages at the back, for numbers starting with 8 and 9, they were almost pristine. He realized that in nature, numbers starting with a 1 occur way more frequently than numbers starting with a 9. Fast forward to 1938, and an electrical engineer named Frank Benford formally tested this on thousands of diverse datasets, everything from city populations to the lengths of rivers. He proved this phenomenon, which is now known as Benford's law, or the first digit law. And today, IS auditors use this exact same mathematical principle to detect anomalies in massive corporate datasets. This brilliantly illustrates how powerful this is in the real world. Just take a look at this Benford's law analysis of vendor payments for Zetech University. In a naturally occurring, completely unmanipulated dataset, about 30.1% of the numbers should start with the digit 1. But look at the observed data for Zetech. Only 25.0% of their vendor payments start with a 1. So, what does that mean? The crucial point is that missing 5%. That discrepancy immediately raises a massive red flag. See, fraudsters usually don't know Benford's law. When they fabricate fake invoices, they just guess randomly, which completely throws off the natural mathematical distribution. That missing 5% tells our digital detective exactly where to start digging. All right, Section 3, Auditing the System Lifecycle. Let's pivot for a second from analyzing data to looking at the actual blueprints of the systems themselves. Why? Because a badly deployed system can honestly be just as dangerous to an organization as active, intentional financial fraud. When looking at the software development lifecycle, the SDLC, we don't just look at the final product. We have to verify the controls at every single one of these 5 steps. Because if you miss a control here, the failures can be catastrophic. Just imagine skipping step 4, user acceptance testing or UAT. If a brand new exam result module goes live without users actually testing it first, incorrect grade calculations could permanently damage the institution's academic integrity. Or look at step 5, deployment. If an auditor doesn't verify that a strict rollback plan exists and a new financial system deployment totally fails, the entire organization might be completely unable to process fees. It causes massive disruption.
But here's the thing. Auditing isn't just a once-a-year event anymore. Welcome to the era of continuous auditing. Think of this as a 24/7 automated security camera for the system's lifecycle. Instead of sampling historical data months after the fact, automated scripts run daily. And look at the terrifying anomalies these scripts can catch in real time. Terminated staff who inexplicably still have active accounts. Grade changes happening in the system without the head of department's approval. System uptime suddenly crashing, or scheduled backups just silently failing in the middle of the night. By catching these issues immediately, auditors shift from just being detectives arriving after a crime to being proactive, preventive guards.
Which brings us to Section 4, locking down the network. Moving out to the perimeter, how do we actually interrogate the very walls protecting the organization? Well, an auditor looks at security through multiple layers, and it's absolutely vital to ensure there are no weak links between them. On one side, we've got firewalls. This is your network-level defense. An auditor will check that the firewall policy relies on default deny, meaning unless traffic is explicitly authorized, it is blocked right at the perimeter. But a strong wall isn't really enough if the safe inside is left wide open, right? That is where OS hardening comes in. This secures the system core itself. The auditor checks that unnecessary services are disabled, default root logins are completely killed, and that complex passwords are mathematically enforced. Because let's be real, admin123 just isn't going to cut it anymore. If either the firewall or the OS hardening fails, the entire network is compromised.
And finally, Section 5, following the audit trail.
So, we enter the deepest part of the system, the database. This is where digital breadcrumbs reveal exactly who did what and when. And what's really interesting about this slide is how all of this comes together into a formal, high-stakes conclusion. When an auditor pulls the logs and finds something suspicious, they don't just wave their hands and say, hey, this looks bad. They structure it using the rigorous 5-element audit finding. Let's walk through this real-world lab scenario from Z-Tech University. First up, the condition. A generic account named App User was found accessing student grades at 2 a.m. on a Saturday. Next, the criteria. The policy strictly states that accessing the grades table requires registrar authorization. Then, the cause. Why did this actually happen? Because generic accounts were being shared among staff, and there was zero multi-factor authentication, or MFA, on the database. Fourth is the effect. This exposes the university to a massive data breach risk concerning student personal information. And finally, the recommendation. The auditor dictates that the organization must immediately implement database-level MFA and destroy those shared accounts. It's logical, it's highly structured, and it is completely actionable. So, we've tracked the digital footprints, we've caught anomalies using Benford's law, and we've secured the perimeter. But as we wrap up this explainer, I really want to leave you with a question to ponder the next time you log into your work email, your banking app, or your student portal. With millions of lines of code and literally billions of data points floating in the cloud right now, who is auditing the systems you use every day? And more importantly, what anomalies are they finding right at this very second? Thanks for joining me, keep learning, and stay curious.